Hello, and welcome to section 11.9 on representations of functions as power series. In this section, we will use a few tricks to expand the catalog of functions that we can express as power series. We will also learn how to integrate and differentiate power series. This will have many advantages, as we will be able to now integrate functions that don't have elementary antiderivatives. Some other classical applications include approximating functions using polynomials and solving certain differential equations. We begin with our flagship example, the geometric series 1 over 1 minus x, which equals the sum n equals 0 to infinity of x to the n, which equals 1 plus x squared plus x cubed, etc., where the absolute value of x is less than 1. Our goal is to exploit the power series expansion of this function to build more examples. Let's take example 1. Express f of x equal to 1 over 1 plus x squared as the sum of a power series and find the interval of convergence. Here is the trick. We wish to make 1 over 1 plus x squared resemble the form of the function 1 over 1 minus x. First, note that we can rewrite 1 over 1 plus x squared as 1 over 1 minus negative x squared. Now the trick is simple. All we have to do is replace x with negative x squared in the power series representation. 1 over 1 minus x equals the sum n equals 0 to infinity of x to the n. Doing so, we have that 1 over 1 plus x squared, which equals 1 over 1 minus negative x squared, equals the sum n equals 0 to infinity of negative x squared to the n, which equals the sum n equals 0 to infinity of negative 1 to the n times x to the 2n, which equals 1 minus x squared plus x to the 4th minus x to the 6th, etc. Now, whenever you have a power series representation of a function, the first question you should be asking yourself is, where is this representation valid? You must always specify the radius of convergence or the interval of convergence. To find the interval of convergence, recall that the power series expansion 1 over 1 minus x equal to the sum n equals 0 to infinity of x to the n is valid only when the absolute value of x is less than 1. To obtain the power series representation for 1 over 1 plus x squared, we replaced x with negative x squared. So we do the same for the inequality, the absolute value of x is less than 1. We get that the absolute value of negative x squared is less than 1, which means x squared is less than 1, and thus the absolute value of x is less than 1. Therefore, the interval of convergence is negative 1 to 1. There are essentially two steps to such a problem. The first step is to make the function resemble 1 over 1 minus x, and the second step is to make the correct substitution in the power series expansion 1 over 1 minus x equals the sum n equals 0 to infinity of x to the n, which equals 1 plus x squared plus x to the third, and so on, where the absolute value of x is less than 1. It is extremely important that you never forget to specify the radius or interval of convergence. Let's do a second example. Express f of x equal to x squared over 4 plus x squared as the sum of a power series and find the interval and radius of convergence. To make this function resemble 1 over 1 minus x, we need to do some work. There are three main issues to deal with. The first is the numerator x squared. The second is the 4 in the denominator. And finally, we have the sign in the denominator. We deal with them in this order. To deal with the x squared in the numerator, we just factor it out. X squared divided by 4 plus x squared equals x squared times 1 over 4 plus x squared. Next, to deal with the 4, we also factor it. We get x squared equals 1 over 4 times 1 plus x squared over 4. And finally, we deal with the sign. X squared over 4 times 1 divided by 1 minus negative x squared over 4. All that remains is to expand 1 over 1 minus negative x squared over 4 as a power series. To do this, we substitute negative x squared over 4 for x, and the power series representation for 1 over 1 minus x. We obtain 1 over 1 minus negative x squared over 4 equals the sum n equals 0 to infinity of negative x squared over 4 to the n, which equals the sum n equals 0 to infinity of negative 1 to the n times x to the 2n divided by 4 to the n. Therefore, x squared divided by 4 plus x squared, which equals x squared divided by 4 times 1 divided by 1 minus negative x squared over 4 equals x squared over 4 times the sum n equals 0 to infinity of negative 1 to the n times x to the 2n divided by 4 to the n, which equals the sum n equals 0 to infinity of negative 1 to the n times x to the 2n plus 2 divided by 4 to the n plus 1. Note that in the furthest right equality, we distributed x squared over 4 into the sum. Lastly, to find the radius of convergence, we substitute negative x squared over 4 into the inequality the absolute value of x is less than 1. We get the absolute value of negative x squared over 4 is less than 1, and so x squared is less than 4, and we get that absolute value of x must be less than 2. Therefore, the radius of convergence is r equal to 2, and the interval of convergence is negative 2 to 2. We now conclude with the most important part of this section, integration and differentiation of power series. We state the theorem that tells us how to do this. Suppose that f of x equal to the sum n equals 0 to infinity of cn times x minus a to the n has radius of convergence r greater than 0. Then f of x is differentiable on the interval a minus r to a plus r, and the derivative f prime of x equals the sum n equals 1 to infinity of n times cn times x minus a to the n minus 1. And the integral f of x dx equals d plus the sum n equals 0 to infinity of cn divided by n plus 1 times x minus a to the n plus 1, where d is a constant. Furthermore, the radius of convergence of all of the above power series expansions is r. So the situation couldn't be any better. To differentiate or integrate power series, you simply perform the procedure term by term. At this point, we issue a warning. One should be careful with the indices when differentiating power series, as the indexing for the derivative starts 1 unit later. If f of x equals the sum n equals 0 to infinity of cn times x minus a to the n, then the derivative f prime of x equals the sum n equals 1 to infinity of n times cn times x minus a to the n minus 1. We now use the above theorem to express even more functions as power series. Example 3. Express f of x equal to 1 over 1 minus x squared as a power series and specify the radius of convergence. The main technique with such a problem is to hope that maybe you are able to either express the derivative or the antiderivative of the given function as a power series. If you can do that, then you can apply the previous theorem to obtain a power series expansion for the given function. Observe here that the integral of 1 over 1 minus x squared dx equals 1 over 1 minus x, which equals the sum n equals 0 to infinity of x to the n, which equals 1 plus x squared, and so forth, where the absolute value of x is less than 1. So to obtain a power series expansion for 1 over 1 minus x squared, one simply needs to differentiate the power series expansion of 1 over 1 minus x. Therefore, f of x equals 1 over 1 minus x squared, which equals the sum n equals 1 to infinity of n times x to the n minus 1, which equals 1 plus 2x plus 3x squared, and so forth. The radius of convergence for the power series expansion for 1 over 1 minus x is r equal to 1, so by the theorem, the radius of convergence for the power series expansion for 1 over 1 minus x squared is also r equal to 1. For our final example, we express f of x equal to the natural log of 1 plus x as a power series, and we specify the radius of convergence. This function does not have a pleasant antiderivative, but notice that the natural log of 1 plus x equals the integral of 1 over 1 plus x dx. So we expand 1 over 1 plus x as a power series. 1 divided by 1 plus x equals 1 divided by 1 minus negative x, which equals the sum n equals 0 to infinity of negative 1 to the n times x to the n. Here the radius of convergence is r equal to 1. We now integrate this power series term by term. The natural log of 1 plus x equals the integral of 1 over 1 plus x dx, which equals the integral of the sum n equals 0 to infinity of negative 1 to the n times x to the n dx, which equals the sum n equals 0 to infinity of the integral of negative 1 to the n times x to the n dx, which equals the sum n equals 0 to infinity of negative 1 to the n times the integral of x to the n dx, which equals d plus the sum n equals 0 to infinity of negative 1 to the n times x to the n plus 1 divided by n plus 1. Note that the radius of convergence is still r equal to 1. Notice that this is the power series of a specific function. F of x equal to the natural log of 1 plus x equals d plus the sum n equals 0 to infinity of negative 1 to the n times x to the n plus 1 divided by n plus 1. So we must find what the constant is. To do this, you always plug in a value of x that makes the power series equal to 0. Here, if we plug in x equal to 0, then we get that f of 0 equals the natural log of 1 plus 0, which equals d plus the sum n equals 0 to infinity of negative 1 to the n times 0 to the n plus 1 divided by n plus 1, which equals d plus 0, which equals d. Therefore, d equals the natural log of 1, which equals 0. The final answer is the natural log of 1 plus x equals the sum n equals 0 to infinity of negative 1 to the n times x to the n plus 1 divided by n plus 1, where the radius of convergence is 1.